Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. I'm going to talk about exact differential equations. And before I get into the details of those types of equations, let me remind you of something from your Calculus 3 class. What's called the differential of a function of two variables Okay, so the differential of a function z, which is dependent on x and y, is given by the following. So we write dz for the differential of the function z is given by the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. And so again, this is the differential of a function of two variables. And for example, let's say I give you a function that looks like this. Let's say z is equal to, again, say f of xy, which is equal to xy squared minus x squared plus 4y. Okay, so there's a function of two variables. Let's compute the differential of that. So the differential would be dz is equal to, again, partial derivative with respect to x. So that would be y squared minus 2x dx plus partial derivative with respect to y, which would be x plus 4 dy. Okay, so again, this would be the differential of that function of two variables. Now, let's keep that off to the side here, and let me define what an exact differential equation is. So, definition. An exact differential equation is a differential equation of the form m dx plus n dy is equal to 0, where m dx plus n dy is the differential of some function f of xy. Okay, so an exact differential equation is first of all, if I have the form m dx plus n dy equal to 0, that equation is exact if the expression on the left-hand side is the result of computing a differential of a multivariable function. For example, let's do one that should be obvious based on what I have written on the board. Y squared minus 2x dx plus x plus 4 dy equal to 0 is an exact differential equation, because we saw that this came from computing the differential of this function right here. Okay, so I know that that is an exact differential equation. Now, what I want to do is basically I want to show you how to solve one of these differential equations. Okay, so let me clean this side up, and then I'm going to state a theorem that says the following. If m dx plus n dy equals 0, then there is a function f of xy where, well, again, the idea is that if I compute the differential of this, I get that expression. So therefore, if I know that the partial derivative of f with respect to x is given by m, and the partial derivative of n with respect to y is given by n. And I'm going to use those two conditions right there to solve an exact differential equation. So let me show you how this works. So for example, I want to solve the following differential equation. I'm going to do 3x squared plus 4xy minus 2 dx plus 2x squared plus 6y squared dy. I'm going to clean this side up a little bit here. Is equal to 0. Okay, let's clean this up because I'm going to need some space to write out the solution. Okay, so I'm claiming that that is exact, and there are tests to determine that, and I just don't want to make this video 30 minutes long, so I can do that in another video, but we're going to assume that this is an exact differential equation. Okay, so solution. What I'm going to do is pick one of these derivative statements, and I'm going to get some information about the unknown function f, and then I'm going to use the other derivative statement to finish finding that information. In particular, let's start with this statement over here, that the partial derivative of f with respect to x is equal to m. Now, within that equation, I know what m is. M is the coefficient of dx, but I don't know what f is. So that means that df dx is equal to 3x squared plus 4xy minus 2. Okay. Now, in order to uncover some information about f, I'm going to undo that partial derivative, which means I'm going to find an antiderivative with respect to x. So f of xy is the integral of 3x squared plus 4xy minus 2, again, with respect to x in this case. Antiderivative with respect to x, I find that the function f that I'm looking for has the following terms. X to the third plus 2x squared y minus 2x. And then since this is an indefinite integral, there's going to be a constant of integration. Keeping in mind that f could depend on both x and y, and then when I take the partial derivative with respect to x, whatever this is goes away. Well, that sounds like it's a function of y. So that means I'm going to tack on g of y, and this g of y, again, is your constant of integration. Okay. Now, what I'm going to do is use the other derivative statements, the partial of n with respect to y is equal to n, along with this function that I know so far to uncover the constant of integration g of y. So let's go ahead and do that. So again, I'm going to copy that down. I know that the partial derivative of n with respect to, sorry, that should be f. That's why I was kind of hesitating there. Partial derivative of f. So this would be the partial derivative of f with respect to y is equal to n. And I know what the function f is, at least, a handful of the terms. So let's go ahead and differentiate with respect to y. I'm going to get 2x squared and then plus g prime of y, and then equals n. Well, n was this expression right here, so 2x squared plus 6y squared. And of course, the 2x squared y, 2x squareds cancel, leaving g prime of y is 6y squared. So that means g of y is going to be the integral of 6y squared dy, which is 2y cubed. And I know that, of course, the constant of integration here would be like a plus c, but I'm going to just continue on with pretending that it's 0. So we'll see why I do that in the end, but I'm going to say that c is equal to 0. Now, putting this together, I see that the solution consists of the following. X to the third, or f of xy rather, consists of x to the third plus 2x squared y minus 2x plus 2y cubed. And the solution to the differential equation actually is the level curves of this function. So the level curves of this function, if you remember, consist of that expression equal to a constant. So x cubed plus 2x squared y minus 2x plus 2y cubed is equal to a constant c. And so the level curves defined by this equation would be the solutions to the differential equation. Okay. Once again, thank you for watching, and please consider subscribing.